Thanks for the intro, Sam. Thanks for being here for the first talk. We talk about strategically robust bidding in first price auctions. This is joint work with John and Balu, who should be here in a second. The motivation for this work is online advertising, in particular display ads. Anytime you go to a website, say a news website or a blog post, you'll see that there are these banners in the top on the side that are showing you the image of the product, trying to sell it to you. These are called display ads. And selling these ads is a very lucrative industry, generating over $100 billion every year. I think we got some of that as EC sponsorship, but how exactly are these ad slots sold? Anytime a user visits a website, what happens in the background is that the platform sends a message to potential advertisers saying, hey, I have this new user, there is associated ad space, would you like to show your ad? And then the interested participants, advertisers participate in a real-time auction, the winner of which gets to display their ad. For display ads in particular, the auction format is first price auctions. This entire process happens in real time, so in the milliseconds between the time that you click on the link and the web page actually loads, and it happens millions of times a day. Because of the fast pace and the large scale of the market, it's humanly impossible to manually enter your bid into each of these auctions. That's Balu, by the way. I'm sorry, my chat. Yeah. So the setup is as follows. Advertisers have high-level objectives, targeting criteria, value per click or impression. They give these objectives to the automated bidding algorithm that then goes out there and bids on their behalf in these auctions with the goal of maximizing total utility. This has become so popular that platforms like Google and Meta themselves that run ad exchanges provide this as a service. So if you're an advertiser that cannot develop your own algorithm, you can go to them and they'll deploy an algorithm on your behalf. So the setup is all, there are advertisers, each of them has an agent, and they're participating in the auctions. Let me formalize the exact problem faced by an auto bidder. Let's focus on a particular advertiser for whom we are trying to design this algorithm. She's going to participate in capital T sequential first price auctions. In auction little t, the following sequence of events takes place. The auto bidder first observes or estimates the value VT that this advertiser has for winning this auction, computed using their objectives and the features of the user. I'm going to assume that the users are coming randomly to the system. So this value VT is drawn from a distribution F, IID in each auction. Based on the value, the advertiser places a bid, ST of VT. The notation is there to emphasize the fact that the bid depends on the value. You can also think of the auto bidder coming up with a bidding function that it's a bidding strategy which maps values to bids. And then it sees the value and makes that bid. Simultaneously, the market participants also determine their actions. In particular, the seller determines the reserve price and the competing buyers determine their own bids. The maximum of these two quantities we are going to denote with HT. I'm going to call it the minimum bid needed to win, not just the highest competing bid. This is a first price auction. So the advertiser under consideration wins the auction if it's the highest bidder and it clears the reserve price. In other words, if STVT is greater than ST, this advertiser wins the auction and pays their bid. Otherwise, they lose and pay nothing. Finally, once the auction concludes, HT, which is the highest competing bid, is revealed to the auto bidder. It's often done on most major platforms, including some Google exchanges. And then you move on to the next auction. Everyone good on the model? So the goal is we want to figure out how do you design these automated bidding algorithms, especially for first price auctions. The way that I described the problem to you on the last slide, you may think it falls classically into the framework of online learning, and you can treat it as such. So you take an action, which is you bid, then you get some feedback, then you move on to the next step. And the idea would be to let me try and learn the best optimal bidding strategy over time that competes good against the best fixed strategy in hindsight. That's a valid approach, has been taken in a lot of prior work. However, what this approach ignores is that this learning problem is embedded in a market. And in this market, there are strategic participants interacting with that auto bidding system. In particular, there's the advertiser that has to report the targeting criteria and the value per click to this algorithm, which is then determined, that then used to compute the value, so they can lie about their value to the auto bidder to get it to give them more utility. This is bad for both parties. The advertiser has to figure out how best to manipulate this algorithm, and the platform loses the ability to gather valuable information about the value that the advertisers have for showing their ads, which is very important for experimentation or for measuring the efficiency of the system. On the other hand, there are the platform or the web page that owns the ad space gets to set reserve prices, and they can try and manipulate your algorithm in order to extract more revenue out of it. Once again, this is bad for the advertiser because they're typically worse off. They lose trust in the system if you're giving them auto bidders that can be easily manipulated. Also, it just makes the system unstable because you have to reserve price dynamically to take advantage of it, and then the learning algorithm is constantly learning, which is bad for inference. The point here is that if you think of this just as a learning problem and try to design algorithms that are great, even optimal for just the learning task, if you deploy them in a market, they can perform very poorly. And one large class of algorithms where they do perform poorly is the class of mean-based algorithms. These are algorithms which, at each point in time, take an action that's approximately optimal for the past. And Braverman et al. Showed that for this class of algorithms, the seller can take advantage of the algorithm by extracting more revenue out of it than the Myerson optimal revenue. So, on average, so you can extract more revenue on average by exploiting the fact that the algorithm is learning instead of the fact that as compared to a strategic agent. Moreover, the advertiser has an incentive to lie to mean-based algorithms. If they misreport their values, they can get more utility. Importantly, FDRL falls into this class. So exponential weights is a mean-based algorithm. And all of the prior work that attained optimal regret, that were doing the best just on the learning task, used mean-based algorithms. So there's a tension here. The algorithms that we do know that get the optimal regret will perform poorly when you deploy them in markets because they can be exploited by both sides. So this raises some key questions. The first one being, well, what about non-mean-based algorithms? And the chief among them is online gradient descent. This is perhaps the most popular online optimization algorithm, and we know nothing about it. Let me emphasize what I mean by online gradient descent, just to clarify notation. Online gradient descent is the eager version of gradient descent. It falls in the mirror descent family instead of FDRL. And here you project every time you take a gradient step. As opposed to FDRL with the Euclidean regularizer, where you project lazily, you let the iterate go out, and then you project when you're taking an action. We know from Braverman et al. That FDRL with the Euclidean regularizer can be manipulated. But these two algorithms, which are identical if you don't go outside the action space, yet we know nothing about how online gradient descent behaves, not even regret guarantees. Secondly, Braverman et al. Gave an algorithm that is strategically robust. Okay. By minimizing a complicated notion of regret called value swap regret. However, in doing so, they lose out on external regret. So their algorithm attains field bus 7/8 as the regret guarantee. Moreover, more importantly, practically, it requires super constant computation in memory at each step. So you were trying to, in order to get the strategic robustness, you're losing out in the core learning problem. This is another question, do we need to do this? Do we need to go for these complicated notions of regret? Or does there exist a simple algorithm that can get the best of both worlds, both optimal regret and be strategically robust to manipulations? In this paper, we give a unifying answer to both these questions by showing that online gradient descent itself, the good old popular learning algorithm that has all of the infrastructure already in place, both in theory and practice, itself is strategically robust and attains optimal regret. Strategically robust, I mean both sides of the market. So the advertiser would not want to misreport their values to online gradient descent. And the company can do no better by manipulating. So it has no incentive to dynamically change the reserve price to extract more. Any questions about the main model of the result? So the outline for the rest of the talk is, first I'm going to describe a concave formulation for bidding in first price auctions, pure strategy bidding in first price auctions. We're going to leverage this formulation both for our analysis, which I'm not going to present here, and the algorithm. We're going to apply gradient descent to this formulation, show that it has all the good properties you need, and then extend it to the setting where you don't know the value distribution and you can still extend that algorithm. So let's normalize values and bits to lie in 0, 1. I'm going to discretize the bit space because it's typically in cents. So you can think of the ith bit being I times epsilon for some.
Yeah. So I want to ask what do you mean by manipulation? Like,
manipulation, the exact way that I defined earlier, the advertiser can lie to the algorithm and extract more utility out of it. And the seller can set reserve prices in a way so as to extract more revenue than Myerson.
So HT will be reviewed to the bidder. Which will reveal to the bid
after the auction.
after the auction.
Yeah.
Yes, manipulation doesn't mean we lie about HT. That is reported truthfully. There is no Byzantine behavior there. Manipulation means you can extract more than when they behave strategically, which is the Myers and Revell. If you do better than that, can in many cases.
Okay. So now let's look at the optimization problem that the auto bidder is solving again and again. They want to maximize utility in this first price auction. Okay. Let's use H to denote the highest competing bid in the auction. The problem where you're working over all bidding strategies that map values to bids is too complicated. It's infinite dimensional. The mapping from the strategy to utilities is not convex. So you can't really deal with that. A simple observation that has been made multiple times in the past before is that in first price auctions, the higher your value, the higher your bid should be. So you don't really need to deal with this infinite dimensional object. All you need to figure out is at what values you should switch from a lower bid to a higher bid, which are the value thresholds. So at BI, I should go from BI -1 to BI. If I know all of the K thresholds at which I should switch, that completely determines the optimum strategy. So I can just optimize over these thresholds. The issue is, even though this brings us to finite dimensions, it's still a non-convex problem. And this is where we make a main observation, which is that you should move to the probability space, also called the quantile space in the pricing literature, where instead of working with these thresholds, you work with the probability with which you bid a value or above. So the probability is taken over your value distribution. In particular, you set PI equal to 1 minus FI. And now if you use PI as your variables, the mapping from these PIs to the utility is a concave. And importantly, it's concave without making any regularity assumptions on the value function. It doesn't have to be MHR or have increasing virtual values, unlike pricing. Once you have this formulation, you can apply gradient descent to it, and all of the OCO machinery applies. You immediately get square root T regret against adaptive adversaries. So no matter how the HT is being selected, it can even depend on the pass. You'll still get square root T regret against the best fixed strategy mindset. In particular, if everyone is learning, you still get square root T. If the environment is stationary, so it's the highest competing bid is drawn from some distribution at every time step, turns out the concave formulation becomes strongly concave, and you can get log T regret here, which is a drastic improvement over the previous best of square root T. And you're pretty much getting it for free here because of the formulation. Finally, importantly, to your point, it is also strategically robust. What that means is no matter how these HTs are selected, even if there's a single seller and a single buyer, and the buyer wants to, and the seller wants to extract as much revenue as possible, no matter how they set their HTs depending on the past adversarially, they cannot extract more revenue out of the algorithm in total than Myers times T plus a sublinear term. So on average, they can't do better than just posting the optimal reserve price at everything. Once again, holds no matter how the HTs are being selected. Issue with this algorithm is that in order to directly apply gradient descent to this concave formulation, you require knowledge of the value distribution, which you may not always have in practice. That's a challenge. We get over this challenge by just pretending that our value distribution is uniform and then applying gradient descent to that, and hoping that if you pretend it's uniform and apply it, it should do well for other distributions. Turns out that is the case, and it gets square root T regret, although you can't get these results by directly applying OCO results anymore. So we give a novel potential function argument. Once again, all of these results hold even for adaptive adversaries. So if everyone is simultaneously running this algorithm, you also get square root T regret. Next, it's also strategically robust from seller manipulation. So if the seller tries to exploit this algorithm, they also can't extract more revenue on average than Myers. Even more importantly, if everyone is running this algorithm and the seller was somehow trying to leverage the interplay of the learning algorithms to extract more revenue from the system overall, they can't even do that. Because the average revenue, no matter how you set the highest competing with, how you set the reserve price, when everyone is running this algorithm, the max revenue that you can achieve on average is simply this optimal single shot Myers. The best thing, again, what you can do is just run the optimal mechanism at every time. There's no point in manipulating these algorithms, it can't be done. Once again, no matter how you select the reserve prices. Finally, it's also strategically robust On the advertiser side, the advertiser can't gain from misreporting their values to this algorithm. So if they wanted to pretend every time their value was 0.8, whenever it was actually 0.2, doing so would not help them, no matter what function they come up with in order to misreport their values to the auto. Okay. And this holds again for adversarial environments. So as an advertiser, I can rest assured no matter what's happening in the market, there is no point in me trying to manipulate my own auto. Conclude, easy versus lazy projections matter. FPRL with the Euclidean regularizer can be manipulated. Right? And even though FPRL can be manipulated, one should not just directly jump to the conclusion that we need other notions of regret, that we need to directly go minimize. There's this huge popular class of eager gradient descent algorithms that you also need to consider, which in this case turned out to be strategically robust. You don't need to minimize swap regret at every time step. There are interpretable simple algorithms that can get you strategic robustness and optimal regret at the same time. And finally, it's just surprising to us that this simple algorithm, the oldest one probably for optimization, already achieves all of the properties that you need. It Pareto dominates the previously known algorithms. It's getting you the optimal square root regret and being strategically robust to manipulation. And we're excited if this gap in the literature where in a lot of problems people have gone directly from showing that FPRL is bad or mean-based algorithms are bad, directly to let's come up with some other notion of swap regret and minimize that. If that can be broken up with this by studying online gradient descent, which may turn out to be strategically robust in other problems as well. Thank you for your time. Happy to take questions.
We have time for a few questions.
Thanks for the talk. I really enjoyed
Thanks.
and learned down from it. Wonder if there's one more sort of robustness result that's hidden away and I sort of missed it. So if if one of the ad buyers is running gradient descent, is it also robust to so you sort of describe the scenario when all the participants in this auction are all running gradient descent and the reserve price setter can't manipulate this algorithm.
Right.
Is it also true that none of the bidders gain by switching to some other algorithm in the presence of these gradient descent agents?
Gain in what way? Like change your algorithm and against gradient descent, you can't get better regret gain.
Not regret, just like payoff. Like I said, would it make sense if for me, like you're offering all the participants in this auction gradient descent, but for some reason I think of something else I could do that would net me a better payoff on average. Is that possible?
Systematically, linearly more payoff seems
Yes.
impossible because of the regret guarantees. It depends on what you.
The regret guarantee is just like an in hindsight guarantee, right? In particular, if I
Oh, you mean like policy regret?
like a policy
Get them to go
yeah,
somewhere else.
that.
We didn't study agent versus agent because I feel like in order to manipulate that, you need to know the other advertisers' algorithm.
Yeah. I mean, I'm assuming that let's assume I know their value distributions and I know that they are running the gradient descent that I was offered in the first place, but I decided not to take.
Yeah, and that you probably also need to know the value distribution. But yeah, after that, we don't study that side. Interesting question.
Okay.
Cool. While the next speaker is setting up, we can take one more.
How important is to know HT at the end of each time step?
To directly apply gradient descent, we like to get the gradient. HT is part of it. You could try and do some important sampling stuff to work it under banded feedback, but we were focusing on can you manipulate it. Also, it is revealed in a lot of platforms in practice. So we just Any other questions?